welcome to the Last Fireflies podcast, in solidarity with all humans and non-humans dealing with climate chaos.
And we're back with another Infospill episode. I'm Robbie.
And I'm Ani.
Two of the regular hosts of the show. So this is the third and last part of our discussion about accelerated warming. Just to do a quick recap, we've talked about the fact that in the last 10-15 years, there has been something changing in the dynamics of global warming. In particular, the rate of warming, so how much it gets warmer each year. That has been changing from around 0.18 degrees Celsius, that has been stable for many decades, from the 70s up until almost the present. And now in the last 10 years, let's say it's more like 0.3 degrees per decade. Maybe it doesn't sound much in terms of actual numbers, but it has a huge importance. And we've explored one of the leading theories by James Hansen and collaborators that say that these changes that we are seeing have to do with aerosols and how the decrease in aerosols from different causes worldwide has led to a kind of unmasking of the true warming potential of the greenhouse gases. And this is what shows up as this accelerated warming now. Now, for today, I thought that we should maybe go in more depth a bit to understand this kind of tug-of-war between greenhouse gases and aerosols. And for that, we will use exactly this analogy of a tug-of-war. And through this analogy, we will try to explore what happens in the scenario that Hansen proposes and some other scenarios also.
So who are the teams in this game?
Yeah, so imagine like a classical tug-of-war game. Like you have a rope and you have two teams which are each pulling the rope, trying to pull it towards their side. So the first team is the hot guys, the greenhouse gases, which are warming the planet. So let's say in the setup, they are trying to pull the rope towards the right. And the second team, the cool guys, are the aerosols, which are not cool. They are toxic and whatever, but they have this effect of also cooling the planet. So aerosols are tugging the rope to the left, and the result of the game, like in which direction the rope is moving, that gives us whether the planet is warming or cooling and how fast.
With who we should keep the score with, which is our team.
Well, I think because both are bad, as we said in the other episode with aerosols, although they cool the climate, they are irredeemable villains also. They destroy our health and whatnot. So none of the team is to vote for. And what we should do is torch the game completely.
Right, but now we have to understand the game in order to dismantle it, no? This is how
Exactly.
we usually fight. Yeah, okay. So let's see how this game is played so we know how to dismantle it further.
That's a very good way of putting it. Generally, the goal that I'm aiming with the Infospill section is for us to try to understand the game or the system, right? In order to dismantle it, because we need to know where we can act, what we can dismantle without having negative effects, etc., etc., etc. So yeah. So let's think of our little game of tug of war. First of all, what determines the strength of a team? So there is the individual strength of each player, right? For greenhouse gases, you would call this the global warming potential of that gas. When we say that methane has 80 times the warming potential of CO2, that means the global warming potential. That's the physical parameter, right? And we need to multiply the individual strength with the number of players on each team to get the full strength of the team. So the number of the players is basically just how much CO2, how much methane there is. Both of these parameters are pretty well-known quantities. The individual strength, the global warming potential, is pretty well known through physics, and the amount of each gas is quite well known through measurements in the atmosphere. Like CO2 level today is 429 parts per million, I think, or something like that. It's very well measured. So the fundamental strength of each team is pretty well known. For aerosols, it's a bit more sketchy because aerosols spend just a very little time in the air. So they are very closely concentrated around their source. And so you need to have a lot of measurements to actually find out the number of guys at each moment, right, in the team. It shifts around very fast. But otherwise, we kind of know also the strength of the aerosol team. On top of this basic strength, there are factors that can amplify the strength of each team. Let's call it here types of gear. Like, people have gloves, which give you a good grip, or crampons, shoes with crampons that both give you, a good grip. And then on top of your force adds more force with which you can pull the rope. For the climate, we would call these amplifying factors or amplifying feedbacks that amplify the basic strength of each player.
Can you give us an example to understand that?
Yeah. So, for example, as CO2 warms the atmosphere, because the planet is warmer, there is more evaporation, so there is more water vapor in the atmosphere, right? And more water vapor also leads to warming. Water vapor is also a greenhouse gas. So, a bit of warming from CO2 leads to more water vapor, and that leads to more warming. So, the result is more warming than you would expect just from the bit of CO2. The water vapor that appears is an amplifying factor. It's not a fundamental cause. The cause is the CO2, which leads to both direct warming and indirect warming through the water vapor. That's one example. Or like with the permafrost. As the planet warms, the frozen ground around the Arctic Circle, right, it starts to warm and it releases CO2 and methane, and those lead also to additional warming. So in the end, the warming from a bit of CO2 is the direct warming, and the additional warming from all of these factors, which we interpret them as feedbacks.
Okay, that's quite clear.
So this is basically what influences the strength of the teams. And another factor which can happen is external factors like wind. They throw a wrench in the mix. Like you have some wind, tornado strength wind coming from a side, and then it either blows the team in one direction or everyone falls down, or like stuff happens that are not dependent on the strength of the teams. It's just some external thing that overrides the dynamics of the game, let's say like that.
And in the context of climate, these kind of external factors are also like wind, or what kind of external factors you are thinking?
It could be wind. Generally, wind is just a consequence of warming, so it's not necessarily an external factor. So for the climate, we would call these internal climate variability. So elements that cause internal variability are stuff like, let's say, this El Nino phenomenon, which we have mentioned in other episodes. It's just basically episodes where the circulation in the Pacific Ocean gets mixed up, reversed, and so the heat from the air does not get pushed down to the deep ocean. So it stays in the upper ocean and the atmosphere. And so during those episodes, the air is much warmer. So when you have an El Nino, you have a statistical random variation in the temperature. The temperature goes up, then it goes down, then it goes up, following this El Nino phenomenon. That doesn't have anything to do with CO2 or methane. It happens even if there would be no man-made greenhouse gases in the air. It's just cyclic episodes that the Earth goes through.
Mm-hmm.
We could also think of volcanoes in this sense, because volcanoes also just erupt from time to time and they influence the climate. After a major volcanic eruption for 2 years, it's slightly cooler, the temperature. And also plane flights are derailed and whatever, and that's an external factor. It has a temporary effect and it disappears. I think this temporariness is characteristic of external factors.
Okay, so practically, if we go back to the teams and like the game with the hot guys and the cool guys, and they're like pulling the rope in their directions, and the factors that contribute to their force to go on one side or on the other are these ones that you mentioned. The strength of the team that is given by how much gear they have, what kind of gear they have, and what type of external factors amplifies their energy towards one direction or another. Then why is it happening now that is accelerated global warming? What's going on? Like the cool guys are losing the battle, or?
Yeah. So that's the question, right? What is happening now and how can this analogy help us try to understand it. So in the analogy, this acceleration would be like the game is on, the hot guys are slightly winning, they are pulling the rope, and then suddenly there's like a jolt. They start pulling very fast in some direction, or like even maybe falling down because of a sudden jolt. And then the question is what is happening? What can cause this happening? There are a few main explanations explored in the literature, and they have to do with these factors that we described that can affect the game, right? First of all, the main explanation given by the IPCC, we said that the IPCC is this authoritarian, that's a Freudian slip. The IPCC is this authoritative body, and all the government programs are based on their reports. So it's important what they say, and they are in denial. The IPCC main line is that all of what we see in the last few years is internal climate variability, meaning that they say that it has to do with a combination of El Nino and other oscillations, random episodes happening in the oceans, in the patterns of the circulation of the ocean and the air.
So practically they blame these external factors that we were talking about. This like, oh, it's just happening because of a specific region or a specific temporary event, and everything is fine because it's temporary. So we just hope for the best. When that external factor will not be an influence anymore, we will go back to whatever it was before.
Yeah, in the game it would be like people have fallen down, right? And they say that the best explanation is that there was a sudden gust of volcano strength wind and it's just pushed everyone down. But they will get up soon. That's kind of their line. So, what would be the consequences of this scenario if this is just random variability? Well, first of all, just saying that it's random variability doesn't mean it's insignificant. It can have very strong effect on regional weather. It can produce droughts, regionally, usually. In some places, it can produce warming. In some places, it might produce cooling. It's hard to say exactly what it will do when and where. But the most important aspect is that there are no long-term consequences. There might be social consequences, but the effect lasts only 2, 3, 4 years, and then it should subside, meaning that the warming levels should come back down to what it was before this event, this external factor appeared. I think at this point it would be good to give some examples that the internal variability of the climate can produce catastrophic impacts, just so that we don't underplay this scenario. So, for example, generally it is understood that in the last 100 years, the El Nino cycle has been relatively weak compared to other centuries. In the 18th and 19th centuries, we had some very, very large El Ninos, and this led to drought in many areas. In particular, when we have a strong El Nino, it can lead to a collapse of the monsoon in India. I'm not sure if you're familiar with the geography and stuff. India gets its moisture from the Indian Ocean below, and this monsoon is like a period when there are strong winds that push the water vapor from the ocean to the continent, and that's where India gets its moisture from. So if the monsoon fails, that means that there's a year with very, very huge drought. There were very huge droughts, El Nino-led droughts, 3 major droughts during the latter part of the 18th century in India. And these droughts, combined with colonial governance, because we always have to look at it like this, combined, they produced famine. Famine is a social phenomenon, right? The drought is a natural phenomenon. Famine is a social phenomenon. So there was these 3 episodes of famine that led to around 10 million deaths each in this period. Then again, at the end of the 19th century, there were also 3 major droughts, which led to famines again, due to the governance of the British Empire in India and their colonial practices. These were episodes where very strong El Ninos collapsed the Indian monsoon, and that led to drought. This had nothing to do with man-made global warming, right? Or it was not a permanent change in the weather patterns. It was just something that happened during those years of the strong El Nino. And then that disappeared, that subsided.
But which also taught us how our governments and like the colonial governments react to this kind of events. But that's just a parenthesis to come back to it when we look at actually what's going on now with the climate.
If you want a reference on this, one of my favorite books is Mike Davis's Late Victorian Holocausts. It's a wonderful book. It has like 3 parts. In the first part, it explores how scientists discovered the El Nino phenomenon. In the second, it connects how the droughts from the El Nino coupled with the colonial practices to produce these famines. And in the third part, it tries to explain how basically the world geopolitical order was actually constructed in this way by this connection of natural factors coupled with colonial practices, which shaped the so-called third world in this way. Parenthesis, but yeah, to get back to our story. So yeah, internal variability can have a major effect, especially regionally. It's not something neglectable. However, studies that have tried to actually link the El Nino to these crazy jumps in temperature in the last years show that it could maybe explain half of it. So it doesn't seem to be the culprit, the El Nino phenomenon. Other kinds of variability are actually an even worse culprit in the sense that many of them are in a stage where they should contribute to cooling, not warming. Like, for example, the solar cycle is also in a minimum contribute to cooling already, if I'm not mistaken, or some other oscillation in the Atlantic Ocean. That's also in a phase where it would normally contribute to cooling. So it's like we don't have a airtight case, but it's beyond reasonable doubt, I think now, that it's not internal variability that is producing this accelerated chaotic warming in these times.
So if we take out the external factor of what you name internally
internal climate variability.
What you name internal variability of the climate,
Yeah.
then what else is there that we are left with?
Yeah. I'm sorry for all these fancy names, but my hope with it is I keep exposing you to them, and then you learn them, and then you will have the tools to understand even when someone talks in more fancy language, or to understand some articles which also use fancy language. Okay, so what other possible explanations are there for this warming? As we explored in the last episode, if natural variability cannot produce these jumps in temperature, then the question is, what is there actually that changed so fast in this time period that could produce these changes? And really the only thing that changed significantly was the aerosol levels, the sulfate aerosol levels, due to air quality restrictions, regulations in China, international shipping. We explored this in last episode. If you haven't listened to it, maybe jump back to that. Now, according to the IPCC, the way that they model the effect of aerosols, they say that they are a small player and thus cannot have a big impact on the whole game.
But isn't that contradictory? If IPCC says that aerosols team are not a big team and doesn't do enough, isn't that meaning that actually the climate is warming because the hot guys are winning?
No, but you are absolutely right. So the hot team is winning because the planet is warming, right? If the cool team was winning, then it would be cooling. But the question is, what is causing this sudden change, this sudden acceleration that we have seen in the last 10, 15 years? Is it because of some kind of sudden increase in the strength of the hot team? Or is it due to some kind of decrease in the strength of the cool team, of the aerosols? Or is it some kind of external factor that is temporarily pushing everyone to the side? Maybe at this point you're wondering, okay, but I've said that only the aerosol levels have decreased, and this could explain this acceleration. But the CO2 is also rising. Why is it not caused by the CO2? Well, the explanation here has 2 parts. Bear with me. So, first of all, let's just simplify and just think about the CO2. So the CO2 level in the atmosphere, if you look at a plot, like CO2 in parts per million over time in the last decades, it's going up approximately exponentially. So it is going faster and faster each year. So it's approximately an exponential curve, but there is some kind of saturation effect, which I will not go into here. But basically the resulting force of the team is not exponential, but it's actually linear. So you would expect a linear increase in temperature due to this exponential rise in CO2. And that constant trend of 0.18 degrees that we have seen from the 1970s onward, right? That was coherent with this picture of exponential CO2, linear rise in temperature. And you would expect the linear rise, the linear trend, to continue, given that the CO2 level is exponential. And so, to our understanding, the CO2 that we see cannot be causing this sudden jolt. And the second thing here, if you dig a little deeper, one more factor that is important here is what is the circulation time of each gas. That's basically, if you look at one molecule of CO2 or one aerosol particle, how much time does it spend in the atmosphere before getting absorbed somewhere or changing chemically or whatever, before it disappears. And maybe you know this, but for CO2, the circulation time is on the order of hundreds of years. Each CO2 molecule spends hundreds of years, maybe 1,000 years in the atmosphere. So that means that if we add a CO2 molecule, right, add a player in the team, they will stay there in the team, pulling on the rope for 1,000 years. So if we suddenly cut the emissions, the team will remain at the same number of players for a long time. Slowly, in decades, the number of players in the team will start to drop off. Some players get tired and they, get married and move off with their lives. But the decrease in the strength of the team will be slow in decades. So even if you would do something drastic with the CO2 now, which we have not done, but like maybe, I don't know, it happened this year and we have not measured it or something. Even then, we cannot see the sudden impact on the temperature. The impact on the temperature is very gradual. It's going to be slow. Even if we cut all CO2 emissions today, the CO2 level will maybe rise a little bit and then start to decrease, the total CO2 level in the atmosphere. But the decrease is going to be slow. We are going to take hundreds of years until it gets back to pre-industrial levels. And so, while what we can control is exactly the emissions of CO2, the consequences of our actions from today will not be visible maybe for decades. That's why it's urgent to cut emissions today, because it's not like we cut them now and tomorrow everything will return back to pre-industrial times. So there's no mechanism through which, as far as we understand, the changes in CO2 could produce this sudden change in the trend of warming. We would expect the warming to continue linearly, as it has done in the past, even though the emissions are growing exponentially. With the aerosols, it's different because the circulation time of each aerosol particle is like a week, 7 days maybe. So I guess in the terms of the of the game, we can think about it like the aerosol team is doing like a tag team. Every 7 days, every aerosol particle is tagging out and another one comes in its place. So then if you would cut the emissions of aerosols, right, the number of players available for the cool team, then after a week, we would see that they all disappear or, the team is cut down very fast. That doesn't happen for CO2. Even if we cut the emissions, so no new players are coming into the game, the ones that are already there, they will last for decades. They will not disappear. While for aerosols, if we cut the new entries to the game, the new players entering the game, the number of players on their side will dwindle fast. In 2 weeks, they are gone. And so, everything is adding up. We are seeing a cut in aerosol levels because of these regulations, and aerosols because of the small circulation time, how fast they are doing their tag team. That means that they can produce this effect in such a short time after being reduced. In 2 years, we are already seeing the effects of those cuts. For CO2, we would see the effect of cuts only in decades' time.
And practically, IPCC says that nothing changes in aerosols. They're small as always, but suddenly, aerosols don't work neither that small version of themselves. So suddenly, they don't make enough cooling in order that the accelerated warming is happening.
Both things need to come together in order for aerosols to be able to have this big impact. One, their level needs to be cut very fast, which we see, and their strength should have been much higher all along. compared to what the IPCC modeled it. Both of these need to be true. If they were just decreased, but their strength was small, then they could not produce the magnitude of the accelerated warming that we see. So both things need to be true.
That's why you're talking about the modeling problem of the IPCC, that it's not only now, it's more like their modeling of the aerosols impact since IPCC exists, let's say, from the beginning. That's why they can't see the issue at stake, because practically the aerosols team started to really drop their capacities, and they don't see that because their models are not seeing the change enough. Did I understand it correctly?
Yeah, that's exactly right. Yeah. And just to point it out again, we are talking about modeling because the actual strength of the teams is not something that we can measure. The temperature and the temperature rise of the Earth, that's a measurable quantity. We measure that with whatever, thermometers around the world. That's a real measurable thing. And we also measure the quantity of each gas, how many players each team has. That's pretty well known. But the gears of each team, that's something that we can try to estimate based on physics, based on equations, but we don't know it very well. Our equations are incomplete. So that's a big unknown quantity. They are modeled, but we don't fully know if the modeling is correct. What we have access to is only the difference in strength of each team, because that is what produces the warming. Maybe I can try to give a numerical example here. So let's say that in the models of the IPCC, the strength of aerosols used to be 10 in some imaginary units, whatever. And the strength of the hot team, the greenhouse gases, used to be 50, let's say. So the difference is 40. And that 40 produces the 0.80 degrees warming trend that we have seen in the past. That's been quite steady. Now, if this accelerated warming from the present tells us that aerosols were always warmer, so let's say in reality their strength is 20, then if we don't adjust the strength of the hot team, then their difference in the past would have been 50 minus 20, that's 30. But that 30 would not produce the warming from the past. So the only resolution to this paradox is if the hot team was always actually stronger than we modeled. So the strength of both teams are modeled, and the problem is we cannot measure the strengths independently. We only measure their difference, their relative strength, let's say. And the claim is that the IPCC got both of them wrong.
Okay, now I understood. I hope that people that are listening to us could follow through also. Okay, and what happens now with the accelerated warming?
Right. So in the hypothesis that the aerosols are producing this acceleration, there are two things that we would expect to see going forwards. First of all, if aerosols suddenly cut down and their cooling effect decreases, it's like half of the team suddenly letting go of the rope. So what would happen? Well, probably all of them would fall down or like stagger or whatever, move around chaotically for a short period, right? This is exactly what we'd expect if you have such a quick decrease or quick disappearance of the cooling effect of aerosols, which has been there in the past, but now it's disappearing. Physically, this is a well-known effect. It's called like a termination shock. The sudden termination of the cooling effect gives a jolt to the system. So we would expect this termination shock kind of behavior to last maybe for a few years. This is driven by the time scale, by the circulation time of aerosols, which has said that it's like a week. So it's something that has a sudden effect and it should consume itself, let's say, very quickly in a few years. So if the emissions cuts were in 2020, maybe we would expect by now to be, at the end of this chaotic period. It's a bit more complex because it has different stages, but the strongest stage is the first one, which should unfold on a few years, maybe 10 years time scale. After that, what will happen? Well, if the hypothesis were true that the hot team was always stronger than we had modeled before, than we have interpreted before, right, through the modeling of the IPCC and other scientists, then the game should stabilize but they should be winning even more than they did before, because they were always stronger than before, just that there was this strong aerosol team which was holding them back. But now there are just some scrawny players left in the cool team, and these big muscly guys in the hot team are pulling very fast. Again, we would expect, because the CO2 is going up exponentially, as I've said, we would again expect a linear trend of warming, but a much higher trend than we've seen before. So before it was 0.18. During this chaotic time, we said that it's 0.3, 0.4 maybe, the speed of warming. After it stabilizes, maybe it will go back a bit, but much higher than before. So maybe 0.25, 0.3, something in that ballpark is what we would expect. This is actually a topic that's a very strong topic of research. For the actual existing climate of the Earth now, what are the gears? What are the amplifying feedbacks for greenhouse gases? And the problem is sometimes quantified in this parameter called climate sensitivity. It's like if you do a thought experiment, take the Earth as it is now, fix every parameter, but double the amount of CO2. Instead of 400, let's say we have 800. But everything else stays fixed. How much would the planet warm? If the climate sensitivity is higher, meaning the CO2 has bigger, better gear, then both the warming associated with that CO2 is higher, but also the warming is faster, like the trend is faster. And if the climate sensitivity is lower, then the eventual warming is lower and the associated rate of warming or the trend of warming is lower. So that's how the climate sensitivity links to this question of the trend and of the acceleration of the trend of warming.
Mm-hmm.
And this is like a big topic of research. Like the IPCC is saying that the climate sensitivity of the Earth system is like average value like 3 degrees, while from Hansen's theory, it emerges that it would have to be around 4.5, maybe higher. That's a very big difference. And Hansen tries to also determine this climate sensitivity in different ways, from satellite measurements, from historical measurements. And he finds that they all point in this direction, that the climate sensitivity is higher than the IPCC is proposing, which is coherent with this theory that he has about this accelerated warming. Like there's two coherent things.
Mm-hmm.
And so if the climate sensitivity is higher, it means that both the warming associated with that CO2 is higher, but also the warming is faster, like the trend is faster. That's how it links to our question of the trend and of the acceleration of the trend, right? And if the climate sensitivity is lower, then the eventual warming is lower and the associated rate of warming or the trend of warming is lower. So that's how the climate sensitivity links to this question of the trend and of the acceleration of the trend of warming. Even maybe more importantly, if we think of our series of episodes on climate tipping points, we said that at a certain point, this tipping point for the climate might be triggered where we inevitably start rolling towards a hothouse Earth state of warming of 10, 15 degrees Celsius. And Hansen's estimates of the climate sensitivity means it's easier to trigger that hothouse Earth trajectory than we thought.
Ouch.
Yeah.
So it's not only about saying IPCC is wrong. Look, we are looking at better ways to analyze what's going on, why the planet's warming so fast in an accelerated way. It's more about like really understanding the risks that we are taking, not actually taking it serious climate action. And compressed time frames also means closer to our lifetime.
Yeah.
We will see the effects in our lifetimes. So it's not 2050, maybe it should be 2040 or 45. That also means that 2030 that we are also looking at as a target might be earlier, which is how earlier? This year, 2026? Already? We should have done what we planned ourselves to do until 2030. If we look at the factors that are influencing the two teams in the tug-of-war that you explained in the analogy of this episode, we can't influence the gears that they have, like how the clouds are influencing the capacity of the aerosols to actually, I don't know how to say it.
To halt the warming, to cool the planet. Yeah.
To cool the planet. Okay. We can't influence neither the external factors like the wind or like volcanoes or stuff that are happening anyway and temporary and so on in the different contexts. We can't stop the El Nino or, these factors that does contribute to warming and so on. But we do have a capacity to influence more aerosols reduction, but especially not more greenhouses. And we just don't need not more, but way less.
Yeah, and if you think about how soon changes in CO2 show up as changes in temperature, right, compared to how aerosols impact the temperature, this is really a key point because we know that the task is to reduce CO2 and other greenhouse gases, right? This is what we control. This is a result of our anthropogenic activity. But if we reduce the emissions with 50%, let's say, in 2 years, the level of CO2 in the air will not drop by 50% next year. It would decline slowly, maybe during decades. So that's why important that we start acting now, because the result of our actions now will only be seen in a few decades. So it has this lag, this inertia. And I think people really don't understand this. Maybe I think there's a hidden thought in people's minds that we are going to fix things. Solar energy is going to take over coal, and then in 2 years after that, everything will be fine. No, everything will not be fine. Even if somehow magically we would achieve net zero overnight, even then the temperature will continue to rise a little bit until the mid-century, and then slowly start to decrease by the end of the century. This is if we achieve net zero by magic. And while we have not achieved net zero, so while we still have some CO2 emissions, during the time the CO2 level in the atmosphere will continue to rise and the temperature will continue to rise, even if slowly. But that's dangerous still because we are already so close to triggering several of these tipping points that we have talked about. So again, the important point is not that everything is lost, but that we need to start doing something now because the impacts will be felt slowly. And I think our minds are maybe not equipped to think in this way, and we are trapped into this sense of safety because of all this good news about renewables and electric cars and batteries and etc., etc. And on the flip side, because the impact of aerosols is seen so quickly, that is why these geoengineering solutions are gaining a lot of traction. If we implement geoengineering solutions like spraying aerosols in the stratosphere or making clouds brighter with aerosols, those kinds of stuff, their impact is very, very fast. They will be felt in a year or two. But they come with different problems, which maybe we'll explore in another episode.
So maybe there are like a lot of scientific rabbit holes on which maybe we went today, but that really argues how come that we are looking at accelerated warming and is not something temporary as IPCC wants to look at it. And that really means climate action now, not later, not in a nice paved way until some years in the future. So we have all the time to do it nicely in our beautiful policies and so on. We need a disruption of the system as it is. Like we need a change yesterday, now. So yeah, if you are convinced that this accelerated warming is an issue at stake and you understand now maybe a bit better how this system actually fuels itself almost, find your local group and start organizing one if not.
Yeah, let's take over from these toxic aerosols. Let's take over in the cool team.
Okay, so this was the last part of the series from the Infospills. And yeah, if you want to know more or is something unclear, write to us. And Robbie will answer because I just put a lot of questions to understand. That's my role.
Be careful what you ask for, though.
This podcast is autonomously organized. You can support us on Patreon if you have like $1 extra in your pocket today.
Are you overwhelmed? Today, we offer you an invitation, rather philosophical maybe. Instead of giving
into the competitive feeling that drives this world, as we explored in the Infospill section, but also the capitalist competitional ways of existence, we propose you connection. We invite you to tune in to your surroundings, intentionally, often. This overwhelming condition that we feel after listening and taking all the bad news of climate change should not be understood as an individual psychological failure. The contemporary circulation of climate information, its scale, repetition, and framing, does not merely communicate facts, it also organizes affect. As Sarah Ahmed argues in The Cultural Politics of Emotion, emotions are not private states, but effects of social and political arrangements. They stick to objects, shaping how bodies are oriented, what they approach, and what they avoid. Within this context, overwhelm and numbness emerge as patterned responses rather than personal deficiencies. So the constant exposure to large-scale abstract representation of environmental crises can exceed our capacity for sustained engagement. We are not only informed by crisis, we are oriented by it in ways that can limit our ability to respond. If affect circulates without attachment, it risks becoming distance. And more exactly, it risks numbness, withdrawal, or paralysis. So our invitation today proposes a practice of reorientation. Following Sarah Ahmed's account of orientation in queer phenomenology, attention can be understood as directional. Bodies take shape through what they repeatedly turn toward. Or, as Adrienne Marie Brown put it, what you pay attention to grows. If perception is structured by what is within reach, then the dominance of distant, catastrophic imagery risks displacing attention from the immediate environments in which life persists. The invitation, therefore, is not to withdraw from knowledge of the crisis or forget about the climate or just take a nice walk and relax, but to redistribute your attention while engaging with the scientific factual information. This can take a minimal, repeatable form to deliberately encounter something living within your immediate surroundings, a tree, a plant, an animal, even forms of life typically disregarded or devalued, like insects, rodents, urban vegetation. The specificity matters less at this point than the act of sustained attention. Such encounters are not framed as therapeutic relief, but as a means of reestablishing perceptual and affective contact with the more than human world, or the places where life persists. We have so much to learn from the resistance that surrounds us, from the capacity to adapt, change, or crack the system of plants, animals, insects, birds. To register what is still living is to give concern somewhere to land. It allows knowledge to become situated rather than diffuse. It makes loss perceptible, not only as abstraction, but as relation. In their book, Joyful Militancy, Nick Montgomery and Carla Bergman are proposing a different political ecology of feeling. They ask, what kind of relations increase our collective capacity to remain present, connected, and active within conditions of violence, exhaustion, and crisis? And what kind of relation diminish that capacity? For them, many dominant political and capitalist structures organize people through competition, isolation, moralism, fear, and depletion. Even activism can reproduce these dynamics when engagement is sustained only through urgency, guilt, sacrifice, or permanent exposure to catastrophe. The term of joyful militancy, then, does not mean optimism or happiness in the face of collapse. Joyful refers instead to practices, encounters, and forms of relation that deepen attachment to the worlds and communities one seeks to defend, while increasing the capacity to act without becoming entirely consumed by paralysis or despair. In this sense, the invitation to connect and re-establish attachment does not eliminate, overwhelm, but it can make it inhabitable. This does not resolve the crisis. It does not reduce its scale or urgency. However, it may enable a different mode of persistence. To remain in contact with what is at stake, rather than oscillating between overstimulation and withdrawal, require practice that sustain attention without exhausting it. Repeated, intentionally encounters with living environments can function as one such practice. They anchor knowledge in experience. Running away from the climate facts does not mitigate the effects of climate change, and we really want to know the facts. That's why we do the infospills. Disconnection from them does not offer protection. Both running away and disconnection differ rather than transform the conditions of our response. Reorientation, by contrast, is a modest but necessary intervention. It reconfigures how the crisis is lived and perceived, and in doing so, may support the capacity to remain engaged over time. The task is not to feel less, but to feel in ways that can be sustained. The task is to remain engaged, humble, courageous, maybe like a dandelion that grows in disturbed environments and cracks concrete and cracks apparently solid structures. If you would like to support our work, you can do that by interacting with and sharing episodes on social media and subscribing to our YouTube channel. And if you would also like to help us financially, you can do that by subscribing to our Patreon or with a one-time donation to Ko-fi. As you know, in recent years there has been quite serious legal crackdown on climate activism in Europe in general, and also a growth of the far right in many countries, which are very fossil fuel oriented. It's becoming harder and harder to do climate activism, especially in places where the movement is very small and hasn't reached the critical mass, like Romania. This has been very difficult for the growth of the movement. As we said, the members of this collective are involved in the climate movement in Romania in one way or the other. So the earnings from this project will go first of all to provide a part-time income for some of the members of the pod, which will allow us to do more work and take more rest in organizing. And after a certain threshold, we both like to redistribute this money to climate groups and individuals doing important work on climate change in Romania and the Balkans and Eastern Europe. And even supporting us with a $2 subscription in this effort would mean a lot to us. Thank you very much for listening and hope to hear you later and see you on Patreon.
Ding 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 ding.